All right, thank you very much. Welcome to API Days. It's such a privilege to be able to stand in front of everyone in this keynote. I think this is the best speaking slot in the entire conference because first day, everyone's fresh, and most importantly, your first coffee has just kicked in. All right, so leading on from that fantastic opening, really opened our minds. I want to talk a little more kind of architectural. I can't help it. I'm an architect. I apologize in advance. But really think about when and where we want to use AI technologies in the work that we do. And I want to start with a little game. And there is a prize. If you win this, you get a free ticket to API Days Australia 2025. So, who am I? I was born in 2023. At the GPT-3 was just out. It was amazing. I was going to be the next smartphone killer. I was on Time magazine's best inventions. 2024, reviews came out. Not so amazing. Bit of a dumpster fire, and then an actual fire when you tried to charge me. By 2025, my entire company had been sold off for parts and IP, and I was an official entrant into the world's museum of failure. What do we think? Who am I? We are indeed the humane AI pin. Generative AI clearly is not always the right answer. AI full stop sometimes is not the right answer. But the key question is, how do we know when it's the right answer? How can we know where and when we should be using what kind of AI? And this is this model, this framework that we're going to walk through this morning to help give you some ideas of how to approach that. Let's start with where. And let's think about the actual solutions that we build, the products, the apps, the services, the platforms, and how they behave at runtime. They could be deterministic code, right, that always works exactly the same way that we intended it to. On the far end, we have the whole ecosystem of deep learning models, including generative AI, which are completely probabilistic. By design, we do not know exactly what they're going to do. And there are many, many kinds of applications somewhere on that spectrum. Our systems, our AI systems, are a balance of certainty and creativity. And sometimes we choose that balance, and sometimes that balance is forced on us. There's a couple of really interesting special cases here. First of all, if I use AI to generate deterministic code, then my runtime app is still deterministic, and that is a really important property for all kinds of use cases. The other thing to think about is we can take the same large language model, that same generative AI capability, and with one parameter, move it up and down this spectrum. So that's very much something that we want to keep in mind. That's the where. What about the when? And by when, we're talking about where do we focus our AI compute? You know, all those precious, expensive, sexy, shiny GPUs. Do we focus completely on pre-training, predefining really specific, really optimized models for particular use cases? Or do we focus on runtime inference, test time compute, reasoning models, computer vision? And again, there's a broad spectrum of use cases across that continuum. AI systems are a balance of training and inference. And sometimes we get to choose that, and sometimes it's decided for us. So we've got these two dimensions, and when we put them together, we get something really interesting. We can have AI use cases all over this. We could be building foundation models, so heavy focus on vast amounts of pre-training, but at runtime very probabilistic. We might be building multi-agent systems, so again, very probabilistic, but a much greater focus on runtime inference. We might be doing diagnostic imaging in medicine, right? So a lot of pre-training, but far more deterministic, right? You don't want to go into your doctor's office and talk to the overly agreeable ChatGPT, and it's like, "Are you sure I don't have cancer?" It's like, "Oh, you're absolutely right." We might also have things like advanced autonomous vehicle perception systems. So obviously a lot of pre-training, but a lot of runtime compute. But again, less, more deterministic. Right? A stop sign is always a stop sign. And in fact, we can see a whole array of AI-powered, AI/ML-powered use cases all across the spectrum. And it's really important to remember that there is value in every part of this field. Right? Don't feel like you have to be building a multi-agent system on top of GPT-5 in order to be doing anything valuable. There is value to be had all across this. That's a really pretty chart, Rob, but what's the point? Well, the point is that when we think about the when and the where, that can shape our strategy for the what. What kind of AI are we using in our systems? And we can think about this in many different aspects. We can think about the end user functionality that our APIs, that our apps will have. Sorry, it's API days. I had to say API at least once. The technical infrastructure and platforms underpinning, the performance of our systems, do they go fast? Reliability of our systems, do they go correct? Compliance, anyone working in any kind of regulated industry, healthcare, defense, finance, compliance, always top of mind. Cost, huge impact. These systems are not cheap. And we as a society are still figuring out how to make generative AI a really productive, really profitable thing to do. Many kinds of risks in how we build our systems. AI solves some, introduces more. And then finally, there's a real skills dimension. I'm far too old and expensive now to care about the tech. My job is to make sure there are humans who can do the work that we're asking them to do. So let's go through each of these in a bit of detail. I am about to show you several slides full of very keynotey, very abstract statements. I am sure that every single one of you will disagree with one or more of these statements in specific use cases. Keep in mind that we're trying to talk about asking the right questions, not necessarily about having the right answers in one slide deck. So let's go on this journey a bit. Functionality, right? If I want to build a deterministic system, right, that runtime solution, it can be very consistent, right? It's always going to work the way I programmed it. It can be very precise, incredibly important in all kinds of fields. But it is inflexible. A deterministic system will only do what we designed and built it to do. On the other hand, probabilistic, the massive advantage that we're having is they appear to be creative and human-like. We can throw them fuzzy human problems and they come back with human feeling, human sounding answers. So much value in that. The ability to handle ambiguity, to ask questions, to clarify, to converse with us, incredibly powerful. But by design, they are inconsistent. And when they are inconsistent, we have real struggle explaining why. It is such a black box. And for people perhaps in any kind of audit, making critical financial decisions, if you can't explain it, it's kind of it didn't happen. Looking at that compute focus, the when, pre-training, we can build very specific models targeted for very specific use cases. We can make those reusable through transfer learning. But if we pre-train, whatever knowledge was there when we did the training, that's locked in forever. It's static. Runtime inference, we get a lot more dynamic behavior. We can make use of that context that we feed large models, that kind of thing. We're into the realm of prompt engineering rather than data science. But you know, we have issues. It's hard to maintain a stable sort of behavior of these systems. So to your point around like the use of evals, right? AI-powered test frameworks, things, very, very important. Technology-wise, deterministic systems, we've been building them for decades. Commodity tech stack, very easy to build, very easy to test, very expensive to scale and maintain. Probabilistic systems, right? Anyone actually sort of just built, like basically written a markdown document that becomes an agent in Claude or something like that? You know, very, very fast to build, adaptive, but much harder to test. We need special purpose, new testing techniques, and we need specialized compute, right? We need the tensors in deep learning models need tensor processing units to accelerate the maths. And that's like absolutely essential. And that does constrain where and what we can put, where we can like use what kind of models. If we spend time on pre-training, technology-wise, we get very optimized models. We can get simpler deployment because a model is just a bunch of floating point numbers in a file at the end of the day. But we are probably going to lock into proprietary, the NVIDIA training stack. That is where data science lives at the moment. If we focus on runtime inference, we have a much broader range of compute options, including some really specialized, really high performance stuff, edge computing, all kinds of things. But that hardware has to be wherever we're going to run the models, and we need a lot more of that hardware. Performance. Deterministic systems, right? We can performance test, we can tune, we can be very predictable. And compared to deep learning models, very, very resource efficient. Probabilistic models, right? Deep learning models can be fast. Every time you do a credit card payment, there is a machine learning model that executes in real time in milliseconds to do real-time fraud detection. Right? It can absolutely be fast, very resource intensive. Transformer models, large language models in particular, anyone with sort of a computer science background, transformers will always be ON squared space complexity. They are monsters. There's some amazing work getting done by IBM, by DeepSeek, and others around hybrid models for that, but it's definitely an issue. When we pre-train, the training can take a long time, but the models tend to be optimized and faster to do what we want them to do. There's also big efficiencies in that batch training process, right? We're using our compute resources in a batch. We're looking for throughput. We're not looking for response times. In runtime inference though, right, we do have that option to get optimized, like we can tune performance of those models at runtime. But you know, anyone who's dealt with a chat bot, with an OpenAI sort of compliant API, that kind of thing, we do see increased latency. There's a lot of compute, a lot of work getting done in the background. We have scalability problems, right? We do not have infinite context that we can send to these models. And particularly with reasoning models, very, very, very spiky response times, right? Depending on how difficult, how much time that model thinks it needs to spend thinking about whatever problem we sent it. Reliability, right? This is the flip side of performance. Again, deterministic systems, have a bit of a leg up here, right? We can, they will work the way we tested them, the way we defined them. We will know why they do what they do. That accountability of how outcomes happen, how transactions are committed, et cetera, right? We know that, and that's really, really important. That's critical in certain industries. But again, we're only reliable in what we tested for. Probabilistic models, very powerful ability to see through noise, small variations in input. Is it raining? Is it cloudy? Doesn't matter, I'm still looking for the stop sign, right? And that ability to generalize into more use cases than what you train a model for. But it is imperfect because of that probability-based learning underneath, the most severe of which being hallucinations. Pre-training is fantastic for reliability because testing is literally built into the training process of a model. So for scenarios that we thought to test for, we know what the accuracy of the model is going to be when we do the training. But we run the risk of making decisions on outdated model, outdated data, bias issues, etc. With runtime inference, we have the ability to ground in data to retrieve ground truth from areas that will help make the outcomes more reliable. Many models can also show us the chain of thought that led to a particular outcome, which can be very, very useful, right? To see how a model reasoned to whatever answer it gave us. Compliance. So this is where we as creators, as builders, might stop making decisions and have decisions imposed on us. Deterministic systems, we have been making deterministic systems compliant with things for a very long time. It's a well understood problem. We know how to do it. We know how to make these systems auditable, how to document them thoroughly. But again, those systems have to be, we have to define them. We have to design them and implement them and verify them to be compliant. Probabilistic systems, right? Again, we're starting from uncertainty, from sort of a source of chaos. And we can put many, many guardrails in. There's fantastic safety, judge LLMs, all these kinds of techniques to improve the auditability, transparency, compliance posture. But relatively, we still have poor transparency of probabilistic decisions, bias in models, both mathematical and cultural bias, very much a thing. Last challenge is compliance itself for AI systems is still a moving target. It changes very rapidly. The technology moves even faster. So what was okay for your use case 6 months ago may no longer be, or vice versa. So that is a real challenge. Pre-training does help with compliance because we have more central control, more central governance over the models and the data used to create the models. But sort of managing compliance of that model over its full life cycle can be difficult. Problems with copyright material, right to be forgotten, sort of data removal, that kind of thing. Right, we have to go back and retrain the entire model. Runtime inference, we're relying more on dynamic filtering, guardrails, that kind of thing, but definite issues probably most significantly with data exposure, particularly when we equip those reasoning models and things with tools. Right? You can imagine an AI agent that has access to your corporate SharePoint and to your corporate email server. How do you protect data leakage out of that? Cost. Huge, huge, huge issue. Deterministic systems have the lowest cost point, relatively speaking, to run. Right? Commodity hardware can go to any hyperscaler on a planet and just say, here's a machine, here's a Lambda, etc. But development and maintenance costs can be higher. Probabilistic systems, we might run them ourselves, we might consume them, we might rent that capacity and pay for usage. So we have the options of consumption pricing, very, very powerful open source models. But at the end of the day, someone is footing the bill for very, very, very expensive GPU compute. And that's shaping the economics of everything around these systems. We can't forget also about the environmental footprint. The amount of power, the amount of water consumed by large AI data centers is a really meaningful issue. Cost of pre-training, yes, we need very large infrastructures potentially, but we can amortize that training cost over a large amount of inference. As we said, if you're if you're focusing on training, you're probably buying lots and lots of NVIDIA kit, right? So you're spending a lot of money. You are in the queue with every other person on the planet to get NVIDIA GPU chips. Runtime inference, the hope is when you consume tokens, when you consume capacity, you're doing that to deliver some value. So there's this, the intent that what you're the money you're spending is much closer to you planning to make some money out of that. You also have many, many more choices for inference hardware. So more competition, lower price points, some really, really interesting, both sort of data center high volume as well as small, lower powered edge hardware, that kind of thing. But again, you're renting that capacity quite possibly. So you're going to give all your money to OpenAI, who is then going to give 5 times as much money back to NVIDIA for the chips. Anyone seen that sort of infographic doing the rounds on social media with all the funding? And we had one of our partners look at that that is literally a bubble. That literally looks like a bubble. Risk, we're almost there. Many, many, many kinds of risk that we should be considering. Deterministic systems, again, we can reason and kind of think about the risks that those are solving and posing, and we're much better at doing that because we've been doing it for longer. Again, explainability, very important for many kinds of risk being generated by these systems. But human error, building systemic defects into deterministic systems, like robo-debt, for example, absolutely still very, very live risk. Probabilistic systems can actually help address all kinds of risk because a lot of risk management is about making sort of these fuzzy, human, intuitive decisions. This feels risky. This home loan doesn't feel right, or this investment feels, and being able to build models, probabilistic systems that kind of distill that intuition into something repeatable, very powerful. But AI models introduce then all kinds of other risks, bias, hallucinations, ESG risk in the environmental footprint. If we use probabilistic systems to make meaningful decisions that affect people's lives, there is a risk that we get false positives, false negatives. And when that decision does fail, how do we explain it? We can get into all kinds of really serious problems. Risk in pre-training, again, the accuracy. We have confidence in the accuracy of the models, and we can get them crazy accurate, right? Past human expert level quite easily. And we evaluate that during training. But just as we have systemic defects in deterministic systems, embedded bias in pre-trained models, definitely an issue. In runtime inference, we can spend more time inferring in order to get to higher quality outcomes, scaling with test time compute, heaps of amazing research about how that is improving the outcomes from these models. Runtime inference lets these models adapt and understand literally the context that we pass in. What is happening, the individual conversations, inputs from users, real-time information from supporting systems. But very, very hard to control the cost, particularly of reasoning models when you don't know how long they're going to think for. and data privacy risks, very important. Last piece, skills. Deterministic skills, that's probably where a lot of us are today, is we are expert in building those deterministic systems. Lots of talent, lots of really good talent, but perhaps declining interest and sort of a dwindling supply of new people learning those skills, right? You get told enough times that AI is going to take all the programming jobs, and eventually you start to believe that. And we're seeing that in undergraduate intakes in the US, for example. Probabilistic, right? Data science education, AI education is exploding. Everyone is trying to learn these skills. China primary school curriculum, they're going to start from age 6 apparently. But right now, definitely a skills shortage, which pushes up the costs and limits how much you can do. Pre-training in terms of skills, you are firmly in data science territory. Data scientists are very rare animals. Really, really good data scientists are sitting on 8 figures at Silicon Valley startups that have $1 trillion more than you do. But incredibly high leverage of those skills. So depending, if you're doing fraud detection for major banks, for example, it doesn't, you can spend a lot of effort, build a lot of skills, very highly skilled team to get that model right, because the value, the impact that they can bring is spectacular. Runtime inference, and this is particularly not so much building the models, but using them, doing the prompt engineering, context engineering. It's actually an easier skills transfer from where a lot of us are today. This is one of the reasons, I'm most excited about agentic AI, is because it's kind of, this is a problem I can wrap my head around. This is a tool set and a development process that I can understand and I can get really engaged in. When we look at AI systems that have lots of deterministic components and do lots of runtime inference, we call those agents. Right, they're app dev and hardcore text templating. A lot of skills overlap. Really, really exciting. Downsides: best practices in agentic, in context engineering, prompt engineering, agentic development, moving very, very quickly. Very hard to keep up. And if you're hosting these models yourself, then you have a real need for MLOps capability, which again is not terribly widespread. So there we are. We've talked about where and when, and how that can help shape our strategy for what? What kind of AI do we want to use? You're going to hear so many amazing people talking about amazing things over this conference. Get excited, get inspired. I would suggest just keep this model in the back of your head. Remember, there is value to be had everywhere across this spectrum. And think about that strategy. What do you need to do? Where do you want to play for your use cases? Where are you going to be forced to play by the environment, the industry that you're working in? I'll leave you with this wonderful quote from Benjamin Franklin that I think sums it up. There is a place for everything, everything in its place. What is the right place? What is the right choice for the work that you're going to do? Thank you very much.